Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the concept solubility, which is in the solutions topic, and along with that, how the solids solubility in the liquids and gases solubility in the liquids is affected by various factors. All these we shall discuss in today's class. So let's begin that. What is solubility and its definition first? So solubility definition is it is the amount of solute dissolved in a specific amount of solvent at a given temperature. So let us analyze the definition of the solubility. So here they said the amount of solute. So solute means here it may be in any of the physical forms of the solute. You can take gases, liquids or solids. Here about the solvent. Solvent also could be in any of the physical forms of the matter. That is, it could be in the gaseous state or in the liquid state or in the solid state. So solute and solvent could be any of these physical forms. The units of solubility basically depends on which physical state you are taking here. If you take the liquids, in liquids, you can represent the solubility as milliliters in liters or milliliters in liters or liters in liters. If you take solids in liquids, you can represent it as a grams per ml or grams per liter. So that solubility is not the constant units. Usually solubility units are is equals to grams per liter. This is what we are standardizing, but solubility units depends on the what type of physical states of the both solute and solvent we are taking to decide it. So now when it comes to the solubility, here the amount of solute, so the amount, here also specific amount. So the amount is not always constant. But whatever the amount of solute you are adding to the specific amount of the solvent, this specific amount of the solvent means it has to be constant. So when you are discussing about the three type of the solutes, dissolution in X solvent, then the quantity of the X solvent could be constant. If you take the constant, then solubility comparison becomes very easy. For example, so let us take the here 10 grams of X is dissolved in the 100 ml of X, 10 grams of A is dissolved in the 100 ml of the X, and here 20 grams of B is dissolved in the 100 ml of X, and here 0.5 grams of C is dissolved in the 100 ml of X. Means here specific amount of solvent have been taken. Within this fixed quantity of the solvent, whatever the maximum amount of solute can be dissolved, that is its solubility. In case of A, 10 grams is soluble in the X 10 ml of the 100 ml of the X. So 10 grams of A is dissolved in the 100 ml of the X. So the solubility of A is 10 grams per 100 ml. Here 20 grams of B is dissolved in the 100 ml of the X, so its solubility is 20 grams per 100 ml. Here is only 0.5 grams of C is dissolved in the 100 ml of the X, so its solubility is 0.5 grams per 100 ml. So here it comparison becomes easy. Now we can say that which is more soluble means whichever is having more amount of the solute in the given amount of the solvent, that we can say that its solubility is more. So here B amount is more in the same 100 ml of the solvent X. So we can say that B is more soluble and its solubility is more. Next, A is 10 grams. So after B, A quantity is more in the same specific amount of the fixed amount of the solvent. So after B, A is more soluble and its solubility is more. And least solubility regarding belongs to the compound C, which is only 0.5 grams of the solute is dissolved. So here the solubility basically depends on the type of the solute and solvent we are going to take, and along with the temperature as well. So temperature also affects how much amount of the solute is going to dissolve in a specific amount of the solvent. Now all these parameters we shall see by taking various examples. So in our today's class we are going to discuss about the solubility of solids in liquids as well as solubility of the gases in liquids also. So here solubility of the solids in liquids. Basically, it depends. As I have taken that, you take some amount of the solvent. So here I am taking the 100 ml of some fixed amount of liquid solvent, which is in the liquid state at a given temperature T degrees centigrade. To this, I am going to add some solute, some X grams of solute. This solute is in the solid state. So to make this solute dissolve in this particular solvent, then it affects by the various factors. So those factors are, first one is nature of solute and solvent. Second one is temperature. Third one is pressure. So let us discuss about the nature of solute and solvent, how this is going to affect the solubility of the solute in a given solvent. So let us take here the concept nature of solute and solvent. Basically, it follows a theory that is like dissolves like. Like dissolves like. So what is the meaning of like dissolves like? If the nature of both the solute and solvent are similar, then they dissolve more. If the nature is dissimilar, then they don't dissolve. Let us take an example here. Both ionic compounds and polar compounds. So both ionic compounds and polar compounds are more soluble in polar solvents. Like water. And if we take covalent compounds, or non-polar compounds, so these are more soluble in the covalent solvents, or else we can say that non-polar solvents like benzene, CCl4, etc. So let us take an example for both of these. Ionic compounds, I am going to take the NaCl. You know that NaCl dissociates into Na plus and Cl minus ions. You can take polar compounds or compounds which are able to form the hydrogen bond if I take the water, like sugar. It is not the ionic compound, but able to develop the hydrogen bond. So these compounds are more soluble in the water. But the same compounds, if you add to the benzene, here they are insoluble in the benzene. And if to this benzene if you add, these are completely insoluble. So here ionic compounds are more soluble in the polar solvents. The reason here is they are having the charges, or else they are able to develop the certain type of the interactions with the solvent here. And in the case of the covalent compounds, so let us take here naphthalene and anthracene. So both are covalent compounds. These are more soluble in the benzene but insoluble in the water. So that says that if the nature of both compound, solute and solvent is same, they are more soluble. And if the nature is dissimilar, example here ionic compound, here covalent compounds. So NaCl is insoluble in the benzene because ionic compound, this is your covalent compound, the nature is different. So that is the reason why we say that like dissolves like. That means if they are having the same nature, then their dissolution is more. Then here, particularly if ionic compound solubility in water is discussed, then we need to discuss one more important thing, that the dissolution of ionic compounds in the water. Let us take the water here. Add NaCl. Na plus and Cl minus ions always present there. The dissolution of ionic compounds in the water depends on two factors. One is the hydration enthalpy. Second one is the lattice enthalpy. So how can we define both hydration enthalpy and lattice enthalpy? We shall erase this part. So let us see here. What is solubility? Solubility means completely the physical state of one solute has to be changed to give the homogeneous solution. So that NaCl has to dissociate completely in the water as Na plus and Cl minus ion, so that no solid state exists. Both ions exist in the aqueous form only. That means we need to separate the Na plus and Cl minus ions from one another. How can we separate? Why they do exist together means there is a strong attraction force between the Na plus and Cl minus ions. You can take any other ionic compound also. So this strong attraction force has to be split first of all. It has to be dissociated so that Na plus gets separated from the Cl minus ions. That means you need to provide some amount of energy to separate Na plus from the Cl minus ions. The energy required to separate these ions away from each other is known as the lattice energy. So here we need to provide some amount of lattice energy. Whenever NaCl is added to the water, one important thing is going to happen, that see here Na plus and Cl minus ions. Even in the solid state, these ionic compounds contain charges, Na plus and Cl minus ions. Whenever it is added to the water, this Cl minus attract the, we know that water molecule is having the partial positive charges on hydrogen and partial negative charge on the oxygen. So this negative charge try to attract this positive charges belongs to the water molecule, so that here water molecules get accumulated around the Cl minus ion. Similarly here, Na plus ion will try to attract this partial negative charge of the oxygen that belongs to the water molecule, so that here Na plus also try to accumulate some amount of the water molecules around it. So during this accumulation process, everywhere that opposite charges get attracted, like this. Partial positive charge on the hydrogen, partial negative charges on the oxygen. So this partial negative charge is attracted towards the positive charge present on the Na plus ion. This attraction, see the attractions are developed. Here also attractions are developed. Whenever any attraction is developed, it is nothing but the bond. that bond always releases some amount of energy. Here ions are accumulated with the water molecules. This process is known as the hydration. So we say that ions are hydrated because they simply get accumulated by the water molecules. So during the hydration process, for every attraction, some amount of energy will be released. That energy is known as the hydration energy. So from all these attraction forces, some quantity of energy is going to release, that is called as net hydration energy. Now earlier we said that this ionic compound, to separate the ions, we need some amount of energy, that was called as lattice energy. Imagine here, just only imagine 10 calories of energy is required to separate Na plus from the Cl minus M. But here hydration energy is 20 calories. This hydration energy is more than the required amount of energy. So when released energy is more than the required amount of energy, so some of this energy shall be utilized by the ion to separate from each other, so that the ionic compound is completely soluble in the water here. If the hydration energy is 9 calories, then this energy is not sufficient to separate these ions from one another, so that it cannot be soluble. That means here we can say one particular form, that if hydration energy is greater than or equals to the lattice energy, then such compounds are, ionic compounds are soluble in water. And if hydration energy is less than the lattice energy, then such compounds are completely insoluble in the water. So the solubility of the solutes in a particular solvent depends on the nature of the solvent also here. Instead of the water, if you take the benzene, then this concept is not applicable. Why? Because in case of the benzene, hydration concept is not applicable. That's why their parameters are different. Example, if we take the iodine, if you add to the potassium iodide solution, iodine is soluble both in CCl4, acetone, like non-polar compounds, and also ionic solvents like potassium iodide. See here, iodine is not soluble in the water, but iodine is soluble in the potassium iodide, aqueous potassium iodide solution. The reason here is iodine can react with the potassium iodide to form the I3 minus ions. That means if the solute is able to react with the solvent, then also its solubility increases. So basically the sending of the particular amount of the solute into the solvent using any of these methods is called as simply solubility. So here hydration enthalpy dominates, then the lattice enthalpy means solubility is observed, otherwise solubility is not observed. So this is the nature of solute and solvent, how it is going to decide the solubility of the solids in liquids. Now let us discuss here one more important thing, that during the dissolution of a solute in a solvent, how many type of the solutions are going to develop? So the number of solutions that we are going to get whenever a particular amount of solute is dissolved in a solvent are of 3 types. Basically 3 types of solutions are there that we can decide as unsaturated solutions, saturated solutions, and supersaturated solutions. So let us imagine here, I have taken the x grams of solute in the 100 ml of the solvent. Imagine I am taking out 10 grams. So maximum this solvent, 100 ml of the solvent can take only 10 grams of the solute, not more than the 10 grams of the solute. So if the less than this amount is dissolved, less than 10 grams in this case, if less than 10 grams, imagine 5 grams of solute I added, but still there is space for the 5 more grams. That means more amount of solute can be dissolved in a solution, then such type of the solutions are called the unsaturated solutions. So the solutions in which more amount of solute can be dissolved because still there is space for the incoming solute. Saturated solution means no more amount of the solute. Whatever is required, that much is already dissolved. 10 grams of solute is dissolved. Maximum extent is already reached. Whatever extra amount of solute you added to the saturated solution, that will not dissolve, simply that settles at the bottom of the given beaker. So it simply gets settles there only, but not the precipitation process. It only settles down. So that is what called the saturated solution. In the saturated solution, one important thing is going to happen, that during the addition of solute, you are changing this physical state of the solute from here solid to the liquid. That process is known as the dissolution. So we are sending the solid solute into the liquid solvent, and finally both together exist as a liquid only. The process is known as the dissolution. So dissolution happens in the unsaturated solution as well as in the saturated solution. To the saturated solution, more than the required amount of the solubility, if you add any extra amount of the solute, that settles at the bottom of the beaker. Then this is called the undissolved solute. Undissolved solute, and this is always present in the same physical state, solid physical state, and some of the solute particles already dissolved, they are present in the liquid state. Now this saturated solution is having the two type of the solute particles. One is the solute particles in the liquid form, and another one is the solute particles in the solid form. So liquid particles have the more random movement in the liquid state because their attractions are less when compared to the solute particles. So whenever they are moving, they may collide with each other and also with the undissolved solute particles. So whenever these dissolved solute particles collide with the undissolved solute particles, means their previous physical state, then they start separating out from the dissolved form. That process is known as the crystallization. So crystallization is an opposite process to the dissolution. Dissolution means solid going to the liquid form. Crystallization means liquid is coming out into the solid form. So that is called the crystallization. So this both process, opposite process, continuously takes place for a long time, and afterwards they reach a stage where the rate of dissolution is equals to rate of crystallization. So what is the meaning of this rate of dissolution and rate of crystallization? Rate in the sense always compared with the time. Imagine 10 molecules are dissolving in a 1 second of the time. That is what it called the rate of dissolution. And crystallization, 20 molecules are coming out from the solution into the undissolved form. That is its rate of crystallization. But at a particular stage where rate of dissolution is equal to rate of crystallization, the number of molecules going into the solution form is equal to the number of molecules coming out of the solution. That means if 10 molecules dissolved, 10 molecules comes out. If 20 molecules dissolves, if 20 molecules comes out. That means the number of molecules in both dissolved form and undissolved form remains same. That means constant, they don't change with the time. That stage is known as the equilibrium stage. So at equilibrium, which parameters are constant? See, the number of solute particles, number of dissolved and undissolved solute particles. remain constant. Second one, so when the number of dissolved and undissolved solute particles remain constant, automatically concentration of the solution remains constant. So concentration remains constant. So what is concentration? The amount of solute dissolved in a given amount of the solution is called the concentration. As a rate of dissolution is equal to rate of crystallization, there is no change in the number of dissolved solute particles. That's why concentration also remains constant for saturated solutions. Now, what is a supersaturation? Supersaturation means, imagine this is a sugar, so that we can take the live examples. So 10 grams of sugar you can dissolve maximum amount in the 100 ml of the water. So 10 grams is reached, that is called a saturated solution. Afterwards, you added some extra amount of the solute that will not dissolve but settles at the bottom of the beaker. Using some spoon, so that you are doing the stirring process. Means mechanically you are applying some force to make these undissolved solute particles to dissolve. So by using some external force, we are making sure that the undissolved solute particles are also going to dissolve. So if this extra amount of solute is dissolved, then required amount is maximum 10 grams it can take. But we are forcing the solute to dissolve. That means more amount of solute is dissolved than the required amount of the solute. That type of the solutions are known as the supersaturated solutions. So here more than required amount of the solute is dissolved. Then now let us try to add some amount of the solutes to all these type of the solutions: unsaturated, saturated and supersaturated. If extra amount of solute is added to the unsaturated solution, it goes into the solution because it has still space, no precipitation occurs. Here extra amount of solute if you add to the saturated solution, there is a chance for the saturated solution to convert into the supersaturated solution by applying the some force. That's why here precipitation do not occur. But whatever you add extra amount of the solute, that settles down. This is different from the precipitation. Precipitation, in the sense, you have to bring the dissolved solute particles into the undissolved form by adding some solute. That is what we call the precipitation process. But whatever extra amount you are adding in the case of the saturated solution, that will settles down, but it will not bring any new particles out. Why? Because they already reached their maximum extent. And this is a dynamic equilibrium. Dynamic equilibrium in the sense, dissolution and crystallization both continuously to takes place. That's why number of solute particles in the dissolved form do not change. So here no precipitation occurs, and moreover there is a chance for the saturated solution to be converted into the supersaturated solution. Then if you add any extra amount of the solute to the supersaturated solution, in this case precipitation will begin. Why? Because already it reached its maximum extent by even applying the force, so that it cannot take no more amount of the solute. At the same time, by adding the extra amount of the solute from the outer side, these solute particles will try to attract the dissolved solute particles, so that more amount of the solute starts separating out from the solution. Finally, the solution will convert into the saturated solution. That's why precipitation occurs only in the case of the supersaturated solutions. So here dissolution means solubility of the solutes in a solvent depends on the factors as well as the quantity amount of the solute also by applying some forces. So this is about the nature of solute and solvent. Let us discuss about the temperature, how this temperature is going to influence the solubility of the solids in liquids. So we shall take temperature effect. So here temperature, basically whenever you are dissolving any particular amount of solute in a solvent, two type of process may takes place. That means it may release amount of energy, so the dissolution may be exothermic in nature, or it may take some amount of energy, so that the dissolution could be endothermic in nature. if the solute nature, it depends on the nature of the solute and solvent. If the dissolution of solute into solvent is an exothermic process. So let us take an exothermic process. So in the exothermic process, when temperature rises, automatically solubility gradually decreases according to the Le Chatelier principle. What is the reason? The reason is exothermic reactions are the reactions where extra amount of energy they lose it. So they don't need any amount of energy, they are losing. So whenever amount of energy is coming out, then they dissolve. Then amount of energy comes out. This process is called the exothermic process. But instead of that, if you add, instead of coming out of the energy, if we give the amount of energy, then the process takes place in the opposite direction. That means dissolution gradually decreases. So for all exothermic reactions, solubility decreases by increasing the temperature. There are some examples for which dissolution of calcium hydroxide in water. It forms calcium hydroxide, calcium oxide in water gives the calcium hydroxide. KOH, when you dissolve in the water, it becomes the aqueous KOH. These are all exothermic processes in which temperature when increases, automatically their solubility in the solution gradually decreases. Next one is endothermic process. So in endothermic process, they need energy. See here, we are sending the energy. So the solute needs some amount of energy to dissolve. Then only it will dissolve more. If you don't give this amount of energy, solute do not have its own amount of energy to go into the solution. That means more the energy you give from outside, more amount of solute can be dissolved into the solvent. That means all endothermic dissolutions are favorable by increasing the temperature. So in case of endothermic process, when temperature increases, solubility also increases. Example, NaCl. When NaCl is added to the water, you will get the aqueous forms of Na plus and Cl minus ions. So this dissolution process is an endothermic process. More the temperature you give, more amount of solute can be dissolved. So that is the effect of temperature on the solubility of the solutes in the solvent. Now let us see the effect of pressure finally. Usually we know that both liquids and solids are incompressible. Solids are completely incompressible. Even you apply the more pressure, the volume of the solids do not change to much extent. That is negligible. Even in the case of the liquids also, you apply the more and more pressure, much change in volume cannot be observed. So that we can say that both liquids and solids are incompressible to the pressure. That's why pressure effect is not observed in the solubility of the solids in liquids, because here both are not affected by the pressure. That's why their solubility is not affected. Now let us see how the gases in liquids are affected by various conditions. Solubility of gases in liquids. So here also, as we discussed in the case of the solids in liquids, here also the solubility of the gases in liquids depends on the conditions like nature of gas and solvent. Condition number 2 is temperature and 3 is pressure. So let us discuss about the nature of gas and solvent. Here, first of all, let us take the solvent like polar and non-polar. So I am taking the water and benzene. benzene or CCl4. So we are going to discuss mainly about the water molecule, and this we shall discuss later. And nature of the gas. So here gases are of two categories. They are easily liquefiable gases and non-easily liquefiable gases. So what are the easily liquefiable gases? The gases which can be liquefied very easily are known as the easily liquefiable gases. Usually the gases with polar bonds are easily liquefiable. Second one is if they are able to form the hydrogen bond, then they are easily liquefiable gases. And third, higher molecular mass. In this condition is subjected to the various gases, that depends. So higher molecular mass is there, means they also can be solved because van der Waals forces are more there. Non-easily liquefiable gases, that means these gases cannot be liquefied very easily. Such type of the gases are known as the non-easily liquefiable gases. So these are not having any polar bonds, completely non-polar molecules. And a smaller atomic size or smaller molecular weight and atomic size. Usually they are the non-easily liquefiable gases. Let us take the example for the easily liquefiable gases. Example, HCl easily liquefiable, ammonia easily liquefiable, SO2 easily liquefiable, etc. These gases can be liquefied easily because they can develop the attraction forces very easily. Non-easily liquefiable gases. These gases cannot be liquefied very easily, like H2, helium, oxygen, nitrogen, argon, etc. So these gases needs even lower temperatures, minus temperatures, then they can be liquefied easily. So easily liquefiable gases are more soluble in the water than the non-easily liquefiable gases, and moreover the gas whichever we are going to take, if it is able to react with the solvent, then its solubility is higher. If it do not react with this solvent, then its solubility is less. Now if we take the hydrogen chloride, so hydrogen chloride gas, when you add to the water, then it forms hydrochloric acid. So it is more soluble. And when you add the ammonia gas to the water, it forms ammonium hydroxide, so that it is again more soluble. And if you add SO2 to the water, it reacts with the water and form the H2SO3, so that is also more soluble. Means easily liquefiable gases not only can be liquefied easily, if they are able to react with the water, then their solubility in the water shall be very high. And non-easily liquefiable gases, these gases cannot be liquefied easily because of smaller molecular mass, smaller atomic size. Smaller atomic size means attraction force is also very less, so that's why their liquefaction becomes very difficult. And if these gases are not ready to react with the solvent, then they are also not soluble in the solvent. So here nature of the gas is affecting the solubility. Similarly, when you take the HCl gas and try to dissolve in the benzene, benzene is a non-polar compound, hydrogen chloride is a polar compound. Then though it is a gas, but it is completely insoluble in the benzene because polar and non-polar, that is what like dissolves like concept here. So non-polar polar compounds or polar gases are insoluble in the non-polar compounds. This is about the nature of gas, how it is going to decide its dissolution in the given solvent. Now let us come to the concept of the temperature. So let us take a diagram here. So this is some water is present along with some oxygen is present in that water. So your condition is, whenever you are heating this, any particular liquid, starting these molecules separate out and they go into the vapor state. Means conversion of liquid to its gaseous form is an endothermic process. That means we are giving temperature. When temperature is given, when energy is given, then only liquid shall be converted into the gaseous state, otherwise it will not convert. So the conversion of all liquids into their gaseous forms is an endothermic process. We are discussing about the dissolution of gases, the solubility of gases in liquids. Means reverse process we need to do it. Means we have to send the gases from outside into the liquid, so that we have to make sure that the gas is dissolved. Then we are doing the reverse process. So the dissolution of gases into the liquid must be exothermic. Why? Because gas molecules always with a higher energy. To convert these higher energy molecules into the lower energy molecules, you need to remove some amount of energy. That is the reason why the dissolution of gases in any liquid is always exothermic process. Now, let us take two conditions. What happens if temperature is increased? If temperature is increased, it favors sending of the gases out of the liquid, so that solubility of the gases in liquid gradually decreases. And what happens if temperature is decreased? If temperature is decreased, that means you are removing the energy, excess amount of energy, so that higher energy molecules can be converted into the lower energy molecules. So the solubility of the gases in the liquids gradually increases. So this is the reason why the fishes, aquatic life, fishes and all these whichever stay in the water, they feel very comfortable during the winter season rather than in the summer season. Because in winter season the temperature falls down, so that the water also gets cooled, so that it will have the more amount of the oxygen dissolved, so that they get the more amount of the oxygen. Hence they always spend their most of the time at the deep of the water during the winter season. And summer season, when temperature rises, whatever the oxygen dissolved, that starts coming out, so they don't get the more amount of the oxygen. They feel completely discomfort. To get the more oxygen, they travel to the upward of the water levels. So they always stay in the upper layers of the water. That is the reason why fishing becomes very easy during the summer season rather than the winter season. So this is the effect of the temperature on the solubility of the gases in solvent, water. Now let us take the effect of pressure. How this pressure can affect the solubility of the gases in the solvent. So the pressure effect, the relation between the effect of pressure and the solubility of the gases was given by Henry, that we call as a Henry's law. So he has taken an experiment in which a liquid is placed and a piston is placed above that, and here some amount of the gas is present like this. So when piston is moved from here to here, that means when you are applying the pressure, initially the gas molecules come close to each other. Again, when you apply the pressure, when there is no chance for the gas molecules to escape, when they have only one chance to dissolve into the water, then automatically their solubility increases. That means initial stages, here gas molecules in the undissolved form, some amount of the gas whichever is dissolved in the water are in the equilibrium stage. By applying the pressure, more gas molecules try to dissolve into the water and new equilibrium is established. Again, when applying the pressure, more amount of the solute can be, that means gas can be dissolved. That means more the pressure you apply, gas has no option to escape, only option to dissolve. That's why gas going into the solution. That means more the pressure you apply, more amount of the gas can be dissolved. Here amount of the gas dissolved into the water or the solvent, we can take it as a concentration. That concentration, now solubility, we can consider it as a solubility. The solubility can also be considered as the mole fraction, as it is independent of the temperature, so that the mole fraction of the gas in the water do not change at a particular temperature pressure. So the pressure mole fraction relation has given the Henry has given the pressure and mole fraction relation. Here we cannot take the molarity or other concentration terms. The reason why we are considering only mole fraction is mole fraction is independent of the temperature, so that at a given pressure, even though temperature changes, the mole fraction do not change, because we are applying the pressure. If pressure is not applied, the gas starts coming out of the solution. So here he has given one relation, that is Henry's law. According to him, the partial pressure of a gas is directly proportional to the mole fraction of the gas dissolved in the given solvent. That means more the pressure you apply, more amount of the gas could be dissolved. Now let us try to replace this proportional symbol using the constant. So partial pressure of the gas is equals to some constant Kh into mole fraction of the gas, where Kh stands for the Henry's constant. And this Henry constant is not constant for all the gases. It depends on the nature of the gas. That's why Henry's constant depends on nature of gas, pressure applied, and temperature. Basically, we can take that it depends on the temperature more than the pressure, so that here we can take the temperature. So how the temperature and nature of the gas are affecting the Henry's constant, let us see here. We know that Kh is equals to partial pressure of the gas divided by mole fraction of the gas. Mole fraction has no units, so that Kh ultimately having the units of the pressure of the gas unit. That means you can take the atmospheres or pascals or bar, whatever it may be. All pressure units can be considered for the Kh. Now, when nature of the gas changes, like here we have taken that soluble gases and non-soluble gases. When more soluble gas you have taken, more shall be the mole fraction. When mole fraction value increases, automatically Kh value decreases. At the same time, when temperature increases, more amount of the gas particle starts coming out. Then automatically mole fraction decreases, so that Kh value increases. That's why Kh value depends on the two factors here, both the nature of the gas as well as the mole temperature of the condition of the experiment where we are confirming this. Now let us see some applications of the Henry's law, where we can apply the Henry's law in the making of the soda bottles or the cool drink bottles. So where you can see that all soda bottles are nothing but the carbonated water. So they take the water and they send some amount of the carbon dioxide under higher pressure. And all cool drink bottles are similar. Only their flavor and taste changes. So for that purpose, they add other ingredients. But basically, they are nothing but the carbonated water. That means carbon dioxide dissolved in the water. So more amount of the carbon dioxide, if you want to dissolve into that particular water, then you need to maintain two conditions. That means you have to apply the more pressure and temperature has to be decreased. That is the reason why on the cool drink bottles, we can see that it was written store under the particular temperature, lower temperature, so that more amount of the gas always stays in the liquid. So in making of there, we can use this Henry's law application. Second one is scuba divers. We know that scuba divers are the persons who go to the deep of the sea for different purpose, adventure and searching purposes. So whenever these persons are going to the deep of the oceans or the sea, they take some oxygen cylinders along with them. So the oxygen cylinders contains both oxygen as well as the nitrogen gas. So when they go to the deep of the sea, above their body, gradually the water level increases. The more deeper they go, the more level increases. When the water level increases, the pressure applied by the water on their body also increases. So when the pressure increases, automatically whatever the gases they have taken, whenever they inhale both oxygen as well as the nitrogen. So both the gases starts dissolving into the blood. If oxygen is dissolved, nothing will happen. Why? Because oxygen can be utilized by the blood for oxidation purpose. But when nitrogen is dissolved, it is of useless because it is not participating in any of the biological activity. So when the person is coming upward direction, so automatically level of the water decreases, pressure drops. When pressure decreases, whatever the earlier nitrogen dissolved in the blood, that starts coming out in the form of these small bubbles. So these bubbles may gather and they may create the larger bubble, which may intervene the flow of the blood, and it may causes sometimes death also. And there is one more thing, that when nitrogen is coming out of the blood, it will give some pain to the body, that is called the bends. So to avoid this, nitrogen is always diluted with helium gas, because helium is insoluble in the blood, or else its solubility is negligible in the blood. So that is the reason why all these oxygen cylinders are always diluted with the helium up to 11%, 11.2% is there. And this nitrogen percent is dropped to the approximately 52.6%. This is the application of the Henry's law. And one more application is there. We know that there are some persons who go for trekking purposes, climbing of the mountains. They take the oxygen cylinders with them. But here reverse process, we can see that. In the case of the scuba divers, they go to the deep of the sea so that the pressure increase on their body. Now when these persons are going for the climbing purpose, trekking purposes, they are going upward direction so that the pressure drops, atmospheric pressure gradually drops, so that when pressure drops on their body, whatever the oxygen they inhale, that may not dissolve in their body because pressure on their body decreases. When sufficient amount of oxygen is not dissolved in their body, automatically they don't get more oxygen for their biological activity purposes, and the thinking of the persons gradually decrease. So it gives some uncomfortable and not able to see clearly also. That is called the anoxia. So these are some conditions. There we can see the application of the Henry's law. And regarding the questions of the Henry's law, we used to see that the mole fraction of the gas is there. Whenever you see some questions, we know that mole fraction of the gas is nothing but number of moles of the gas divided by number of moles of the gas plus number of moles of the solvent or solution. Solvent we take it. Remember that if you want to solve the question early and get the approximate close answer, then try to avoid to take the number of moles of the gas. So directly take the mole fraction of the gas is equals to number of moles of gas divided by number of moles of the solvent. Why we are avoiding means the number of moles of the gas, the solubility of the gases in the liquids usually shall be very less. So if you take this value also, that is negligible when compared to the total number of moles of the solvent. And if you add that, you will get the fraction values and it becomes difficult to solve the question. So that avoid the taking number of moles of the gas in the denominator, so that directly you can get the mole fraction of the gas. So dear student, this is today's class. I hope you understand. We shall meet in the next class. Thank you one and all.